Deriving confidence intervals using hypothesis test inversion. In the standard asymptotic tests in a Stats 1 class, there is a one-to-one correspondence between hypothesis tests and confidence intervals. In this video, I'm going to show you how to derive confidence intervals using the method of hypothesis test inversion to illustrate this correspondence. So we begin with the one-sample z-test. We will assume that x is normally distributed and the population mean is unknown, but the variance is known. So we are going to take a random sample from random variable x, which is also the symbolic notation for this normally distributed population. And let's call this random sample x1, x2, x3, x4, all the way up to xn. Now x1 we will call the first observation. X sub 2 we will call the second observation. And x sub n we will call the nth observation or the last observation. And this is ordered in time. That is the time in which the observations were collected. Now, let's hypothesize under the null hypothesis that the population mean is equal to some specified value, which we'll call mu naught. And the alternative hypothesis is that the population mean is not equal to mu naught. So this is the standard two-sided, or sometimes called the two-tailed, z-test. And it's the z-test not only because of these hypotheses, but because we're dealing with a normal distribution with unknown mean about which we are hypothesizing and known standard deviation or variance. So all these together makes it the two-tailed z-test. And we'll do this at some significance level, which I'm just going to call alpha. Now, if you recall from your one-sample z-test, I'll draw a little picture, actually. What we have is we have 1 minus alpha area inside, and we have alpha over 2 area in the tails. We call this negative z sub alpha over 2, and we call this positive z sub alpha over 2. Now, don't forget that this is an alpha, and this is a 2. Some of my students sometimes get a little confused, but keep that in mind. So what we're doing here is here we fail to reject the null hypothesis. And here, in this region here, we reject the null hypothesis. I can make this a little bigger, but not too much. And here in this region, we reject the null hypothesis. So what we're basically doing is we fail to reject the null hypothesis when our z-score is between negative z sub alpha over 2 and positive z sub alpha over 2. So this is when we fail to reject the null hypothesis. Now, the confidence interval actually gives you the region of this parameter value that we hypothesized, this mu naught, for which we failed to reject the null hypothesis. That's one of the interpretations of the confidence interval. It's not the one that we teach students first. First, we just say, well, you know, the confidence interval has a 1 minus alpha times 100% chance of capturing the parameter that we're trying to estimate. But then when the student reaches a slightly higher level, then we start making the connection between the hypothesis test and the confidence interval. And that's what we are going to do here. So I want to remind you that Z, I'll write it over here, Z is equal to X bar minus mu naught over sigma sub X bar. So if that's the case, what we can do is we can substitute this value of Z in this inequality. And what we're actually going to do is we are going to solve this inequality for this hypothesized parameter value. And that is actually going to give us our confidence interval using this method of hypothesis test inversion. So I'm going to write this out for you guys on a separate piece of paper so I can do it nice and large. So we have negative Z sub alpha over 2 is between X bar minus mu naught over sigma sub X bar is less than Z sub alpha over 2. Now I want you to see where this came from. Negative Z sub alpha over 2 is less than Z. Negative Z sub alpha over 2 is less than Z. Now this is Z, right? Is less than positive Z sub alpha over 2 is less than positive Z sub alpha over 2. So it comes right from this. And what we are going to do is we are going to solve this inequality for mu naught. So let's do it. Let's do this by first multiplying this by sigma sub X bar. And it looks like my green color isn't coming out too well, so I'm going to use my regular pencil. But I do want to show you that this sigma sub X bar will cancel over here and leave this numerator. So what we have is we have negative Z sub alpha over 2 sigma sub X bar is less than X bar minus mu naught is less than positive Z sub alpha over 2 sigma sub X bar. Now we're getting there. We're not there yet, but we're totally getting there. So now what we have to, again, what we want to do is we want to solve for this mu naught. We're getting close, but we're not there. So now what we're going to do is we're going to subtract X bar from all members of this inequality. All right, so we're going back to high school here. So here what we have is we have negative X bar minus Z sub alpha over 2 sigma sub X bar is less than negative mu naught is less than negative X bar plus Z sub alpha over 2 sigma sub X bar. We are close, 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 close. Now, we don't want to solve for negative mu naught. That would be kind of silly. We want to solve for positive mu naught. So what we're going to do is we're going to multiply this entire inequality by negative 1. And we're doing this in order to get rid of this negative, because a negative 1 times a negative mu naught is a positive mu naught. So we're doing that because we want to do this. Well, if we multiply this inner term by negative 1, we have to multiply all the terms, which would be these outer terms. So negative 1 times negative x bar is a positive x bar, and this minus turns into a plus, and this is z sub alpha over 2 sigma sub x bar. All right, good so far. Now, don't forget, when we multiply an inequality by a negative number, we do have to flip the inequality symbol. You learned that in high school, right? Okay, we're getting somewhere. So now we have negative 1 times a negative x bar is a positive x bar. And we have negative 1 times a positive z sub alpha becomes negative z sub alpha over 2 sigma sub x bar. So I want you to notice that this is the larger member of the inequality, and this is the smaller member of this inequality. If you look at this, you should be able to see this, because with this greater than sign, remember, like the large mouth, you look at this as like a little mouth, so the mouth is to the larger side. So in mathematics, when we write a compound inequality such as this, when we want to say x is between a and b, where a is less than b, we write it this way. This is a way of saying x is between a and b. And I want you all to notice that these are both less than symbols. So when we have this inequality over here, you'll see that these are both greater than symbols. But this is the lower bound of the confidence interval, and this is the upper bound of the confidence interval. So the way we're going to write this is we're going to write this as mu naught is between, again, less than symbols, because we read from left to right in math, right? We have less than x bar minus z sub alpha over 2 sigma sub x bar, and x bar plus z sub alpha over 2 sigma sub x bar. And you should recognize this as the confidence interval. Now, we write it in a more compact way. We write this as x bar plus or minus z sub alpha over 2 sigma sub x bar. And that's exactly what we have here. Here's the x bar minus z sub alpha over 2 sigma x bar minus. And here's the x bar plus z sub alpha over 2 sigma sub x bar plus z sub alpha over 2 sigma sub x bar. So what we have just done is we have just successfully derived the standard confidence interval for the population mean of a normal distribution with sigma known. In other words, known standard deviation or known variance. But the important thing that we have here is we have derived this confidence interval by first looking at the hypothesis test. And this is called the method of hypothesis test inversion. Because what we did was we solved for those values of mu naught which would result in failing to reject the null hypothesis. Now, I want to write this down for you so that you have this idea written. So in summary, we formulated the standard one sample ztest, where the null hypothesis is that mu is equal to some hypothesized mean, against the alternative that mu is not equal to that hypothesized mean. And from this, what we did was we realized that we fail to reject the null hypothesis when z is between negative z sub alpha over 2 and positive z sub alpha over 2. And what we did was we realized that x bar minus mu naught over sigma sub x bar is equal to z. So we stuck this in here and we solved for mu naught. And what we got, we got that mu naught was between x bar minus z sub alpha over 2 sigma sub x bar and x bar plus z sub alpha over 2 sigma sub x bar, which is the same confidence interval formula, x bar plus or minus z sub alpha over 2 sigma sub x bar, that same two-sided confidence interval formula that we always had, that we were given kind of by fiat, really. We see that this corresponds to the hypothesis test perfectly. So then the question that I typically get from students at this point is they say, well, professor, okay, you did this with a two-sided, a two-tailed hypothesis test. But if I recall, professor, you taught us one-tailed tests also. You taught us right-tailed tests, and you taught us left-tailed tests. How come most textbooks don't have right-tailed and left-tailed confidence intervals? And the answer is, well, some do. And there are right-tailed hypothesis tests and left-tailed hypothesis tests. So they have to be right and left-tailed confidence intervals. And so now I am going to show you how to use the method of hypothesis test inversion to get right-tailed and left-tailed confidence intervals, so that given a confidence interval, you can test even a right-tailed or a left-tailed hypothesis test. So here we go. Let's start out with a right-tailed one-sample ztest. And so we assume that X is a normally distributed population with unknown mean and known standard deviation or variance, whatever you like thinking in terms of. And let's formulate this in the standard way. So the null hypothesis is that mu is equal to mu naught, and the alternative hypothesis is that mu is actually greater than that hypothesized mean. And we'll just do this at, a significance level, which we'll call alpha, just like we did before. And I'm going to draw you a little picture of this so you can see exactly what's going on. So here, in this region over here, we're going to reject the null hypothesis, right? And in this region over here, we're going to fail to reject the null hypothesis. And if you really want to be technical, you know, this goes out to infinity, negative infinity, and this goes out to positive infinity. And this is 1 minus alpha area under this z distribution. So this is a z. Make that look a little better. Look a little funny. So this is a z. And alpha is your significance level. That's not a 519, that's an SIG, significance level. And so what we do is we fail to reject the null hypothesis when, now here, this over here is z sub alpha. It's not alpha over 2. We're not dividing this into two tails. This is only a one-tail test. So this is positive z sub alpha. That's what this critical value is. So we reject the null when z is greater than or equal to z sub alpha, but we fail to reject the null when z is less than z sub alpha. Now remember, when we derive the confidence interval, we're solving for the value of mu naught such that we fail to reject the null hypothesis. I think I'm going to write this out for you again. So when we derive a confidence interval by the method of hypothesis test inversion, we solve for the values of the hypothesized mean such that we fail to reject the null hypothesis. Okay, that's not so bad. So let's write this out then. So for this right-tailed test, I'll write right-tailed confidence interval continued. So for this right-tailed hypothesis test, we are going to fail to reject the null hypothesis when z is less than z sub alpha. And of course, z is x bar minus mu naught over sigma sub x bar. This is also known as the standard error of the mean, is less than z sub alpha. Okay, right? Here we write z is less than z sub alpha, but we know that z is x bar minus mu naught over sigma sub x bar. This is sometimes called the standardization theorem. Okay, so we have that. And so now, just like we did for the two-sided case, we are going to solve for the hypothesized mean. So the way we're going to do this is we're going to multiply both sides of this inequality by the standard error of the mean. Because what that does is, here, this and this cancel, and we're getting a lot closer to getting mu naught alone. And of course, what we do to one side, we have to do to the other. So what we have here is we have x bar minus mu naught is less than z sub alpha sigma sub x bar. All right, we're getting there. Now, of course, we want to get this mu naught alone. We're solving for it. So we're going to subtract x bar from both sides. And here we have negative mu naught is less than negative x bar plus z sub alpha sigma sub x bar. Okay, fine so far. And now, since we're not solving for mu naught, we're not solving for negative mu naught, we're solving for mu naught. So what we have to do is multiply this entire inequality by -1, because that will remove this negative symbol over here. So what we have is we have that mu naught. Now don't forget, when you multiply both terms of an inequality by a negative number, you have to flip the sign. Don't forget, you have to flip the sign. And this becomes positive x bar minus z sub alpha sigma sub x bar. Now, how do we write this in interval notation, which is the way that most math professors would want you to write this, using interval notation? So this is saying that if mu naught is greater than this value, if all the mu naughts that result in us failing to reject the null is greater than this value, this is actually a lower bound. So this is a lower bound of the confidence interval. So that means, using interval notation, our confidence interval is going to start at x bar minus z sub alpha, not z sub alpha over 2, because we only have a one-tailed test, right? Sigma sub x bar. But with this interval notation, we have a lower bound, then we have a comma, and then we have to go to an upper bound. But there is really no upper bound. See, mu naught can be as large as you can conceptualize. And the largest element in what mathematicians call the extended real number system, the largest element in the extended real number system that a human being conceptualizes, is symbolized by this symbol called infinity. So if we write this in standard interval notation, this is called infinity. So in standard interval notation, the right-sided confidence interval goes from x bar minus z sub alpha sigma sub x bar to positive infinity. And this is the formula. So this here is the right-sided confidence interval. The right-sided confidence interval for a normal population's mean with the standard deviation known, sigma known. Now, if you look at this formula, it's not so different than the two-sided formula. If you look at the two-sided formula, you have x bar plus or minus z sub alpha over 2 sigma sub x bar. Now you have plus or minus z sub alpha over 2. Here you have x bar just minus, and it's z sub alpha. There's no dividing the type 1 error rate by 2, because it's only a one-sided confidence interval. But this is the confidence interval that you get using the method of hypothesis test inversion. So we can use this confidence interval to test a right-sided hypothesis. In other words, let's say we wanted to do the z-test, and we wanted to do it using the confidence interval method. Well, we would formulate the confidence interval using this formula over here. And then if this formula captured our hypothesized mean, which we're just calling mu naught, then we would fail to reject the null hypothesis. And if the confidence interval failed to capture or cover, you could use the word cover, this hypothesized mean, then we would reject the null hypothesis.